Welcome back. This is section 19.4, Entropy Changes in Chemical Reactions. For all of its looking hard, this is seriously easy. No problem. You can do this. You can do this. Okay? So remember that entropy, delta S, is simply the amount of randomness that you have. Okay? And you're going to have a table of every substance and what their molar entropies are in joules per mole Kelvin. Okay, so it does not matter what it is. You can look it up. If you're doing something on Alex, then there'll be a data table for that. If you're doing something in your book, the end of the book, there's a table for this. If you're working on the net, you can pull this off of the net, no problem. Okay, so every substance that is actually a compound is going to have some type of a molar entropy and remember the little degree mark means that it's at standard temperature and pressure, and simply making, when you make it, how much more random is the products than what you made it out of. So taking the first one in the table, hydrogen gas, is it more random to have hydrogen as a gas than the hydrogen that you made it out of? Every single one is measured, and then there's an entropy for each one. So really all you're doing is you're taking the balanced equation. So in this case, 1 mole of nitrogen gas plus 3 moles of hydrogen gas yields 2 moles of ammonia gas. So each one of those has an entropy. So each entropy is multiplied by the number of moles in the balanced equation. So you're going to take all the products. So in this case, I've got 2 ammonia molecules, or 2 moles of ammonia. I take 2 moles times however many joules per mole Kelvin that is, right? So it'll be, so if I look up ammonia, I'm going to look to the side, it's 192.5. I'm going to do the products minus the reactants. That's all I'm doing. So at the top in red, I've got brackets here because that first brackets is your products. 2 moles times 192.5 joules per mole Kelvin. That's all of that together is what your products are. Okay? Now you're going to subtract the sum of your reactants. And the first reactant was nitrogen gas, but there's 1 mole of it, so it's 1 times 191.5. And then I'm going to add to that 3 times, that's 3 moles of hydrogen gas, times its molar entropy, 130.6. So when you multiply those, add the sum, and then subtract the reactants from the products, in this case, you're going to have a negative 198.3, which means it's actually more united, or it's more orderly in the products than the 2 gases that made it up, which means that if it were to happen automatically, it would have to happen, you would have to finagle with the temperature and see whether it could still be spontaneous or not. But in terms of practicality, this is simple, and I hope you get it.